Good afternoon, everyone. My name is Nanda Ravindran, and I'm responsible for the technical sales team at Edgecore. So for today's presentation, I'm going to talk about tuning of an AI fabric, and I'm talking about the scale-out fabric here. So, is it okay? Yeah. Okay, so Edgecore team has been focused over the last year or so in benchmarking the performance of an AI fabric or an AI network. We were one of the first ones to introduce an AI switch, a white box switch, an 800 gig switch. And since then, the teams are involved in several POCs, some deployments. And one of the key challenges that we always come across is, hey, we are tuning. The performance is, not up there. There is something still need to be done. And this is where, I spent some time sitting with the engineers trying to see, hey, what do you guys do? What are the key things that you are working on, and how are you making it happen? And the entire presentation here that I have is from engineers who did this in their labs, trying to configure SONiC, trying to tune different parameters, and come up with the most optimized performance of an AI fabric. So before I talk about the tuning challenges, we all know AI workloads are different, right? I don't need to go more detail. Low entropy, elephant flows, very high density traffic, very large bandwidth requirement, and there is possibility of several elephant flows, and then also the flows have very low variation, causing load balancing issues. So these are well-known issues. And what are the fixes? An ideal network, a lossless network, would have the least latency, and then it would be evenly balanced and providing the most optimal performance in a fabric. And what the team was doing is they were enabling and tuning the following features in SONiC. They were, working with Rocky V2. They were working with priority flow control and ECN, and they were also configuring DLB. So having said that, what was the need for repeating this? Every time you go and, I'm tuning, the performance is not there. We made these changes and there is a difference in performance. So what is going on? So we realized that every time there is a change in the network design, there is a change in the topology, there is a change in the NIC cards being used, or there is a change in the transceiver or optics or cables or whatever, there needs to be some tuning always needed. And so this is a challenge, and I want to show what the team was doing, and we want to see how can we optimize, how can we work together as a community to make this a more automated solution so that all of us can benefit. So here is the test topology that the team was using, and we have 6 Edgecore AIS 800 gig switches. All are OSFP 64 ports. They're all based on Broadcom Tomahawk 5 chipset. The software they were using is a SONiC release a distribution based out of 2023-11. And we, it's a non-blocking configuration. We were using all Ethernet optics, Edgecore optics here. This is a test bed where things were configured and tuned, but we also had other equipment from other vendors, but the process and the methods are the same. So in order to set up a AI network and simulate all kinds of AI workload traffic, the challenge is, you cannot do it in a customer setup or in a place where you have already the GPU servers, and there are several unknowns. It's very important you have the ability to benchmark the performance, at least of the fabric, in a lab before you go on to, a POC or a customer deployment. And that is what this setup is constructed to do. So what the team does is, they configure. I just want to let me mention, we use a Spirent equipment, a test equipment, which can simulate or emulate AI workloads. It is a very important piece of this setup. It has the ability to generate the full life cycle of an AI workload. It can do measurements. It can do the calculations necessary, and it can also do collective communication functions, that you have one setup where you get all the results and you know how the fabric is performing. So at the bottom, I list all the data size, the DSCP value, and the collective communication pattern, and the measurements that this equipment was doing. So let me quickly go into the PFC configuration first. So the PFC configuration, before we apply any, I noticed that before any profile is created or a mapping is done, the team reloads the QoS. Then they set up 3 traffic profiles. One is a profile that maps the DSCP, essentially for the Rocky video traffic, to a queue or a traffic class. And then they map the traffic class to a queue, another profile. And then they map the traffic class again to a priority group. All this, they picked all these 3 here, but essentially those are the 3 profiles created first. And then all those 3 profiles are applied to an interface under test. So you can see, all those profiles that got created were applied. And then there is one function done to bind the ingress and the egress lossless profiles, 2 default profiles that they bind, one to the priority group and the other to the queue, one on the ingress and one on the egress. After all this is done, then the PFC is enabled. So once we're done with the PFC, we go into ECN. Here it's simple. You create a WRED profile, and on WRED profile, you set up an ECN mode. There is a minimum threshold on the queue, there is a maximum threshold on the queue, and then there is a drop probability. So this is repeated, and fortunately the test equipment can repeat after every test. You can set it up, and it repeats it for different probabilities, different thresholds, and it would give out results. So what this graph means here, you have a queue at the bottom. As packets start filling, when you hit the minimum threshold, until you hit the minimum threshold, nothing is marked. Everything is passed without any ECN marking. And once it crosses the threshold, then it is dependent on the code bits that come in the ECT. Depending on the bits that come, either it is left untouched or it is remarked. Lastly, after the maximum threshold is crossed on the queue, then all parts are marked for congestion. So what happens here, basically, the receiver sees that there is a congestion, and then informs the sender, and of course, all the basic stuff that congestion is avoided. This, we will see how it interacts with the PFC in the subsequent slides. Next is the DLB configuration. There are 3 modes. The most relevant modes, actually, I should say, are the hash mode and the DLB eligible or the Flowlet mode. And the spray mode is something that is available. It's available in SONiC, but the test equipment does not have the ability to reorder packets. So, even though we have in the test, it is not something, some of the results are not, relevant. Hash, very easy. This is a standardized hash way of load balancing. The flowlets are, sub-flows within a flow. Essentially, whenever there is an inter-packet gap an increase in the interpacket gap, it's an opportunity to identify that it is a different flowlet, and then you can use that to rebalance. And this is something, it's a good tunable parameter, because it's too far, then load balancing it's too large, then load balancing is not that great, but it needs to be very optimized, and this is a point that can be tuned. Okay, now coming to once it's tuned, now we have both PFC and ECN parameters set up. The first thing is, there is one test done with just the PFC, and interestingly, with PFC, it gives only PFC. It gives the best results in the setup. The reason being, PFC is very what should I say? The response time of PFC is very quick. It responds quickly, and then in the setup, you always see that just enabling PFC is sufficient to get the the least job completion time and the best bus bandwidth. So, but in real life situations, you would see that PFC can cause deadlocks. It is always crucial you enable PFC with ECN and then do the deployment. So now coming to, once you enable ECN, you always want to look at the queue status, how much the queues are getting filled up, and then based on it, you may want to first set the minimum threshold, look at the queues, then set the maximum threshold, and that is how you end up tuning for the most optimal performance and keeping an eye on the job completion time and the bus bandwidth. Last is the drop probability. That again, it's done on different probability percentages. So we will just review that in the next slide. So here again, following up on the previous slide, you set the thresholds, you measure drop probability for a few percentages, 1%, 5%, or the 10% measured in here results. And you would see that, for 1% and a minimum threshold of 2 megabytes and a maximum threshold of 10 megabytes had the best job completion time and also had the best bandwidth or the throughput. So next we continued the the DLB performance, and here we just want to show why an 800 gig switch tends to perform better than a 400 gig switch as far as AI workload is concerned. You can see that we try to use 800 gig port as it is, and then split the 800 into two 400 gig ports in a breakout mode, and then used it. And we also had one setup where we used we filled traffic only to 80% of the port speed. As you can see with 800 gig links, definitely both the job completion time and the bus bandwidth tends to be better. 80%, it was just for reference. You will never want to keep the total throughput on a port lower than what it needs to be, but just shows that when there is room, performance always is better. Link failure. Link failure does introduce a significant drop in performance. We simulated for one link failure, one link down, two links down, and then we see that the performance goes down significantly with one link and then progressively goes down with two link failures as well. The Flowlet mode tends to perform better than hashing in all failure situations. Another test with VXLAN and without VXLAN. VXLAN, is needed in AI. If multi-tenancy is needed, then VXLAN becomes important. So we see that in spite of an overhead added, the job completion time and the bus bandwidth almost identical. Very rarely there is a difference. The performance with and without is almost the same. No change at all. Lastly, we did DLB performance under different collective communication scenarios. We used three scenarios. One is all-to-all 4x8 with XN. And then we used without PXN and then a ring all reduce. So with PXN, this is a mode in which the traffic flows from the GPU to the NIC without the CPU involvement. It goes through the NVLink and the PCIe. So there is this mode called PXN, which eliminates the spine. There is no spine to leaf traffic. And you would see that it gives the best performance irrespective of the load balancing ability, load balancing mode. You see both job completion time and the throughput being the best with when PXN is enabled. The hash, the hash mode does encounter collisions but does recover. The Flowlet also encounters collision but recovers much faster when it identifies a new Flowlet. So lastly, the call for action. Doing this repeatedly with all changes and not every time if a fabric needs to be set up and tuned, then we need a way to work together and come out with a set of specifications, maybe methods and best practices where we can tune AI fabrics. Automation, something that we come out with should transcend the design, should transcend connectivity types, should transcend the endpoints or NICs. And also, this collaboration, should find a way to automate. We have tried to do it ourselves, some automation, but I think, community can drive it and all of us can benefit. Lastly, we made some strategic decisions recently. Edgecore now is a pure play open source SONiC provider, further strengthening our commitment to open infrastructure and also accelerate adoption of SONiC. We do collaborate with Broadcom and deliver enterprise SONiC or an out-of-box experience, offering a robust and open source distribution designed for all use cases, including AI. And you know where to find us. Thank you. Any questions? Yes?
1 second, I will give you my. Thank you. No. You can hear me because
Can you turn it on? Yeah, okay, thanks.
Yes.
So you tested the regular or traditional ECMP using IP source destination, TCP or UDP for source destination. As far as I know, there is now a new DLB mode available on SONiC, which is called Enhanced ECMP, where you can go deeper into the packet to look for the Rocky V2 QP ID. Did you test this, or do you have any plan to test this?
Saying this is already in the community?
It's already there. As far as I know, I think it's already there. Yeah.
So do you know which distribution it is there? Because it's not, this is something we can have the team test on the same test bed.
Definitely not 2023-11. Maybe it's a bit old, but in the latest 2024, 5 or 11, it should be there, I believe.
Yeah, definitely we will connect, and I do want to understand and see, what the the enhancement is, and if it is in the community, it definitely helps.
It would be interesting to see the difference between enhanced CCMP and DLB and packet
DLB.
train.
Okay.
Yeah, thank you.
Okay. Thank you. Any other questions? Okay.
No question.
Yeah. Thank you. I give 5 minutes back.